So,
Okay,
hi, so hi, I'm Cheryl. I'm also a second year PhD student at St Andrews working with Ian. So today I'm going to be talking about stellar radiation feedback, and I will present here for the first time my new algorithm for optimizing the RHD scheme in Phantom. Right, so stellar feedback is a very important aspect in all stellar formation simulations, especially the ionizing radiation, which is coming from the massive stars, because these radiations are known to be the source of the extra regions, and the expansion of extra regions can sweep the surrounding gas and trigger the collapse and hence the star formation. Or it can do the opposite by destroying the cloud. And so it's very important to develop techniques to accurately and efficiently simulate these feedback and incorporate them into the simulations. Right, so the way which I've been using for adding the radiation into, my simulations, it's also a Monte Carlo method, but it's not the MC-FOST. It's this code called the CMacIonize, which is developed by Bert and Kenny here at St Andrews. The first person who coupled Phantom to CMacIonize is Maya Petkova, not me, who was a PhD student of Ian as well a few years ago. So her RHD scheme works like this. I'm guessing this is somehow similar to the MC-FOST as well. But anyway, so within Phantom, in each time step, it'll take the particle's positions and smooth lengths and mass, and then give it to CMacIonize by calling an interface. Then within CMacIonize, it will map the particle's densities onto the Voronoi grid, so kind of similar to MC-FOST as well, and it will do the Monte Carlo simulation. And then afterwards, it will map the ionic fractions of the grid cells back onto the particles and then give this back to Phantom. So within Phantom, if a particle has an ionic fraction of over half, then it will heat the particle and update its internal energy. So Maya's work was mainly focused on this bit, which is the mapping bit, like that, the mapping between the particle density and the grid cell density. And the way she did it is by using this expression here, which is the density at any arbitrary point in SPH space, and then integrate it over the volume of each Voronoi cell to get the average density within that cell. So this is a really perfect density mapping method. It's the most accurate thing you can ever do. But at the same time, it can be quite computationally expensive, as in the time taken to do the mapping can be quite comparable to that of the Monte Carlo simulation itself. But if we actually look at the ionization of the particles inside a simulation, so for example, this is just a uniform box with a single ionizing source placed in the middle. The colors are showing the neutral fractions. Then actually, only this bit in the middle is ionized and heated, but the rest, these yellow ones here, they are effectively sitting there and doing nothing. So this is what motivates my project, and that is to move it up the tree, just like how the forces are done, so that we can be less concerned about the regions which are far away from the source and only focus on the ones which are close to it. So what I mean is, I'm now doing a tree walk relative to the source location, extracting those tree nodes and then turn them into pseudoparticles, which is actually fine, because if I go back to this slide, because this method is valid with any arbitrary sampling points in the fluid, as long as we know there is Y, Z, X, M. So we do actually have a little bit of freedom in tweaking the resolutions in different regions of space, but still apply the same density mapping method. So going back, so now instead of passing all the individual particles to CMacIonize, I'm now only passing the pseudoparticles to it. And by doing that, I'm effectively significantly reducing the number of points that I need to do the mapping, which would then reduce the computation time as well. So just to show you how the real thing looks like, this diagram is only for illustration, it's not a real science plot. So now I'm plotting the mass of the particles, which is same in a uniform box around a source in the middle. So the ones in the middle, those are still the individual particles. So same as the original version, same as the one on the left. But on the outside, I've lifted it up to higher level tree nodes, which obviously has greater masses. And doing this is actually fine because if I show you the neutral fractions of the same plot, this ionized region can be completely unaffected at all. And actually, I've defined 3 regions around each source. So on the inner ring, I have the R part, so that's a radius within which I will get the individual particles. And then on the outside, I have the R leaf, so that's a radius within which I will get the leaf nodes. And the rest, those are the higher level tree nodes. And in situations where there's multiple ionizing sources, this is how the tree nodes will look like. So the tree will only be walked once for all the sources. Okay, but now there's a problem. Like, of course, extra regions will expand. And at some point, the ionization front is going to move to the outside. And in that case, it will then become very poorly resolved, which is not desired. So this is why I've then turned it into an adaptive system. So I'm using the ionic fractions returned from CMacIonize to adjust the tree walk. So the idea is this: if a node is ionized but is pretty big, then I'll open the node and I'll push it down by 1 level, and then I'll call CMacIonize to try again, and I will repeat this until all the ionized nodes are now sufficiently small, so i.e. that they're now all highly resolved. And if the leaf nodes are still too big, then I will push it back down to particle level by simply increasing that radius for extracting individual particles. So this is now a video showing you the outputs after implementing this adaptive system. You can see how the pseudoparticles evolve as the extra region expands. This is now set to the highest resolution, so the ionization front is expected to be on particle level. And you can see how this resolved region is just around the ionized particles, so not so much, not so little. Okay, I need my cursor. Somehow it just disappears every time I fix the video. Anyway, so this is how the algorithm works. So within the time step, I'll take the particles, I'll do a tree walk, and I will extract the pseudoparticles. And then I'll call CMacIonize and feed it into the Monte Carlo simulation to do the simulation and retrieve the neutral fractions of the pseudoparticles. So now afterwards, I will check the node sizes and their neutral fractions against some parting criteria to see if there are any nodes that still need to be opened. If there is, then I'll feed it back to the tree walk and it will go again. And if there isn't, that means we're now all done. That means that now the ionization front is now fully resolved. And by then, I will actually update the particles' internal energy and then move on to the next time step. But obviously, it will be very inefficient. We have to repeat this iteration again in the next time step. So I've actually implemented an extra mechanism in the code that will let it remember how high it was on the tree by the time it got to the last iteration, and then give it to the next tree walk so that it doesn't have to iterate again to find the ionization front. This mechanism works even after the tree reboots, so even after the node indices have changed across time steps. And this algorithm has actually worked pretty successfully because in my simulations, normally this iteration would only need to occur in the first time step. Then afterwards, it will no longer need to iterate. Occasionally, once or twice, following the expansion of the extra region, but not super rapidly. Okay. So just now I've mentioned that using the pseudoparticles for the density mapping method requires the XY we know the positions and the mass of the tree nodes, but we don't know their smoothing lengths. And so here I am solving for it as well. The way I did it is just by using the number density, because this formula here no longer applies if the pseudoparticles have different masses. And so I'm using this original form of the smoothing length, where the number density n is just equal to the sum of the kernel. And I'm solving these two expressions using Newton-Raphson. And I've also got bisection as a backup. So just to show you the outputs, this is how it looks like. Obviously, the nodes on the higher level nodes will have a longer resolution lengths as expected. And when I have the extract of the system set to 1.1, then the average number of neighbors is about 55. So this is done separately from the particles. So this is only amongst the nukes. And I actually made a little neighbor find to go with it as well, which requires the nuke indices. So the tree has to be all indexed. But this can have a little bit of an overhead. So normally, if the number of nukes is not super large, then for now, I will simply do a brute force, which is also very fast. Okay. So just to show you a bit of the initial results I had from testing this new set of codes, there's not much since I've just finished the codes like 2-3 weeks ago, but I will show to you that they're working okay. So the test that I've been doing is called the star bench test, which is a set of benchmark tests used for validating the different red hydro codes currently available, established by BISFAS et al. So the test is on the D-type expansion of the H2 region, which is a very well-studied problem for several decades. So the test is just very simple. It's just by placing a single ionizing source in a uniform box and look at how the ionization front evolves. So here's the results. This is now plotting the evolution of the ionization front radius for a simulation run where I am using all individual particles, the blue one, compared to one where I am using those pseudo particles, which is the red one. And you can see that those two agree very well with each other, meaning the pseudo particle system is working okay. Although I'll be honest here, this thing actually doesn't really agree with the Spitzer solution. I don't know why, I'm yet to figure that out. But given that the same happened to the original version as well, means it's likely to be a problem to do somewhere else in my simulation, but not in those, well, not specifically in those new set of codes. And just to show you how much improvement this algorithm has made, so this is now plotting the CPU times taken around those two simulations, and using pseudoparticles is about 3 to 4 times faster than doing it with all individual particles when the ionization front is on the highest resolution. Of course, it's also dependent on other parameters too, say like the tree opening angle, or like the radius for extracting the individual particles and leaves. And so if I'm letting the ionization front to be on a slightly lower resolution, say like if I'm leaving it on leaves, then I can actually speed this up even further. So just to quickly conclude, so I've shown it to you that using pseudoparticles, using tree nukes as pseudoparticles is a good way to optimize these kind of radiation problems. The computation time will greatly reduce, and but at the same time keeping the simulation results highly accurate. Right, so that's the end of my talk. Thanks for listening. That's a short one, and hopefully there's a lot of time for discussions.
Do we have any questions, Cheryl?
I actually have a question for people in the room. Is that allowed?
I think so. Go ahead.
Yeah, the thing is, I've just found out the existence of MCRT yesterday, because I have not, like, frankly, I have not heard of it at all, and I have not seen it in papers, nor have I heard it from any of the academics in here. So,
Crystal.
So my quick question is just: do you think will be do you think it's a possible direction to try and apply these kind of things to the MCRT as well? Just thinking.
We can try, but MCRT doesn't really deal with ionization.
Right.
So I'm not completely sure it's going to be very useful for what you're trying to do.
No, I'm not sure what exactly the MCRT does either. But from yesterday, I heard that you're also coupling it for doing the radiation. I was just wondering, because I have not really looked into it.
Yeah, I think the main difference with CMacIonize is that it's mostly designed to do ionization, while MCRT doesn't really look into that. But
all right, okay, thank you.
And there's no the advanced mapping that Maya is doing. We never implemented it in MC-FOST either.
Yeah.
Because it's slow, mostly. I think that's the other difference.
Yeah, okay. Well, I'm very happy to stick with CMacIonize, but I was just wondering, got a bit curious yesterday after listening to that.
Oh, I should just briefly comment that we're actually using that mapping for numerical relativity with SPH.
Yeah. Am I using it for relativity?
Yeah.
No,
Well, I'm
I
using
have.
it for relativity.
No,
Yeah.
I have not really looked into the GR bit in the code, so I'm not really exactly sure what that thing does and what's the difference compared to the normal, the regular phantom.
Right. Do we have any other questions? Daniel has one.
So I was curious about, so this exact mapping thing with the exact integral, how much do you break that by using these like pseudo particles? So do you still retain the advantages of doing the mapping exact rather than doing something more approximate?
Yeah, that's the thing that I've been thinking, and this is exactly the reason why I've kept that region around the source. It must be on particle level. So I'm only lifting the ones on the outside, lifting up to the higher level tree-nix, but on the inside, for those immediately, well, especially those ones immediately around the source, those must be on particle level. Otherwise, it just defeats the purpose for using the exact mapping rather than using those other approximations.
Yeah, so just to clarify, so the one thing that we did actually at the last one of the Phantom workshops that Maya attended was that she implemented the exact mapping in Splash to grid. So in the interpolation routine we use if you want to map the SPH into a 3D grid. And so Spencer has been working on that using what Maya did to use it for numerical relativity. So you'll hear a bit more about that later in the week. But there is, that's the other application of this exact interpolation, but also some people are using it by default because Maya contributed that into Splash. So if you do Splash to grid, it does use Maya's algorithm for, yeah, which is really nice.
Yeah, it is. I saw it in the CMacIonize. Wow.
All right. If there are no further questions, let's thank our speaker again.
Thank you. So let's stop sharing.